Hello everyone, welcome to this workshop. It is really nice speaking to you all and I appreciate your presence and your interest. As you may know, my name is Mohammad and I'm currently pursuing a master's in AI. And in this workshop, as we move forward, I will be breaking down the concept of transformers for you. We will explore some essential components of transformers such as attention layer or precisely self-attention layers in the first part of our workshop. This kind of topic have gained a significant attention in recent years and have made market across various types of machine learning applications. And we are going to talk about all of these kind of things at the first part of our workshop. And in the second part of our workshop, we will talk about point clouds, and we will dive into point clouds, and we're going to see how we can use transformer in the field of point clouds, how we can use them to perform some tasks such as classification and segmentation. Okay, before we delve into detail and before we begin, let me know, have you got my voice clearly, or is there any problem you would like to tell me about this workshop at the beginning? Thank you. Let's start with machine learning. After seeing OpenAI's latest amazing events and their latest achievements, the world of machine learning has become even more interesting. And in my opinion, one of the fascinating aspects of working in machine learning is its constant evolution and innovation. Every few years, a fascinating and a groundbreaking advancement emerge that can challenge or maybe change our understanding of what's possible. Unfortunately, today we're going to talk about transformer, and we're going to walk in a little part of this wonderful world. And we're going to talk about transformer. I can say transformers have been one of the key concepts of machine learning in recent years. As you know, transformers are versatile models capable of performing different tasks such as text generation, text translation, even coding, solving difficult problems in biology such as protein folding, and these kind of difficult tasks. And if you have come across popular machine learning models such as BERT, T5, GPT-4, GPT-4o, and others, it is essential to know almost all of them are built on the foundation of transformers. And to stay ahead in the world of machine learning today, we need to know about transformers and we need to understand transformers. The first part of our workshop will be based on this article, Attention is all you need. And unlike RNNs and LSTM, transformers rely on attention mechanism, eliminating the need for recurrence. And this unique architecture allows for parallel processing, making transformer more efficient and faster to train. And now let's say what exactly is a transformer. It is the main question that I'm going to talk about in the first part of our workshop. And let me illustrate with an example. Consider the following two sentences. Server, can I have a check? And looks like I just crashed the server. In these sentences, the word server has different meanings based on the context, and the self-attention mechanism enables the neural network to understand the word by considering the surrounding word and providing a contextual understanding. When the model processes the word server in the first sentence, it may focus on the word check to differentiate between a human server or maybe a machine's machine, maybe mail server maybe. And in the second one, it may concentrate on the word crashed to identify the server as a machine. So now attention can make sense here, but we will talk about it more later. Imagine we have an English sentence. The agreement of the European Economic Area was signed in August 1992. On the other hand, we have got its translation, French translation. Unfortunately, I don't know anything about French. I don't know an alphabet of French, so don't worry, I don't know pronounce it for you. But I can explain this chart. The lighter the color of the square, the more attention our model is giving to that word. Noticeably, the attention doesn't always follow a diagonal pattern. For instance, when translating European Economic Area into French, the model pays attention in reverse manner due to the word order differences. Therefore, our model can understand the surrounding context. It has a contextual understanding. Again, we have got a dog scenario. Let's consider this image scenario. I don't know how much it can be useful here, but at least it is interesting. Suppose we are analyzing image to classify dog breeds. You can observe what the model focuses on. It's dog's noses, dog's ears, somewhere else, I don't know. But obviously the attention helps the model distinguish between different dog breeds. We briefly explored the concept of attention. Let's delve into how transformer networks learn and understand its architecture. We're going to talk about this structure, and from here, this part of our workshop will be a little bit technical, but don't worry about it, we'll continue step by step. We'll dive into the details little by little. And we're going to see how these components work together and interact together, obviously. At a high level, transformer consists of encoder and decoder, as you can see here. However, in reality, we've got 6 decoders and 6 encoders, but let's consider just one of them to understand it easier. And each encoder includes a self-attention layer, focuses on the sentence itself, and a feed-forward neural network. And on the other hand, each decoder has 2 self-attention layers and 1 feed-forward neural network. The efficiency of transformer comes from its parallel processing capability. We input all the words simultaneously into our network, and each word is compared to every other word within a sentence. It allows for communication between the words within a sentence. Now let's discuss embedding. This concept includes both inputs and outputs. Embedding serves as a way to represent word as a vector of a specific length. In this transformer architecture, 512 length vector is used, as mentioned in the original paper, but it can be adjusted, we can change it. Transformers lack recurrence. They can't understand the order of the word within a sentence. They can't understand the position of the word within a sentence. But by incorporating positional encoding, we can provide the model with more information about the position of the word. So this problem has been solved. At the end of the decoder, there's a linear layer followed by softmax. These layers help to transfer the decoder's output into the format that we can interpret it, and it is common in neural networks and you are familiar with them. But essentially the output becomes a vector with a length equal to the number of the word that we have got in our vocabulary, and each cell in this vector indicates the likelihood of the corresponding word being the next word in the sentence. There are a couple of additional features that enhance the performance of transformers. One of them is the normalization layer. These layers help standardize the output of the sub-layers. The normalization technique employed here known as layer normalization, which is essentially advancement over batch normalization. And another important aspect of transformer architecture is the skip connection. And if you take a look at the original architecture diagram, you'll notice arrows connecting some of the sub-layers, and maybe actually all of them. These arrows connect all of the sub-layers. Information that doesn't pass through the either self-attention layer or feed-forward neural network is directed straight to the normalization layer. And this design helps the model retain important information and ensure it progress relevant data. Yeah, it is the architecture of transformer. I think we review all of them. And okay, before we continue, have you any question? Is there anything special you would like to tell me about the first part of our workshop? Multi-attention versus mask multi-attention. Great question. If you have got any other question, ask me and then I will answer to all of them. Okay, about your question, thanks for your great question. There's no difference. Basically, there is no difference, and the differ is how to use them. I will explain more later. But now, as a short answer, I can say it. There is no difference. There is no special difference, but it's about how we are using these structures. Do you introduce any articles in the field of image? Not really. Thank you for your question, but your teacher or your professor can be the best person who can introduce you a better article. I'm going to talk about point clouds, and I don't want to talk about image. I'm not very great in this field, so I prefer to not tell you anything about image field. You can ask this question from your teacher. Anyway, thank you for your questions, and let's continue. However, there are 2 standout ideas, as I said before, from the original transformer paper that truly revolutionized transformers, I can say. Positional encoding and multi-layer attention layer. Positional encoding is different point cloud, so I don't want to discuss it too much. But about multi-headed attention, about your question, in original architecture, as you mentioned, there are 2 types of multi-headed attention layers: regular multi-headed attention or multi-headed attention, and mask multi-headed attention. Despite their name, they essentially perform the same function. There is no specific difference, whether an encoder or encoder. This difference lies in how they compare words. If I'm gonna explain this part, I can say in standard multi-headed attention layer, each word is compared to every other word within a sentence. On the other hand, mask multi-headed attention layers, only preceding words are compared to the given word in a sentence. Let's start the process again, with more detail, step by step. First, assume we are here and we have transformed the words into vectors, and we have also added the positional encodings here. Then in this step, the embedding vectors are multiplied by specific matrices to produce query key and vector values. Query key and vector values are our famous vectors. You can see them everywhere that we're going to talk about transformers, and we can produce them here again. These vectors are created by multiplying the embedding by three matrices that we trained during the training process. For instance, multiplying x1 by wq produces q1, query 1, our first query. The initial steps here, computing a score for each word in relation to every other word in the sentence. To achieve this, we calculate the dot product, the query vector of the each word with the key vector of all other words. Do this. For instance, to find the score between the first and second word, we calculate the dot product between the query vector of the first word with the key vector of the second one. But importantly, these calculations are conducted in parallel, allowing us to process all words simultaneously without waiting for sequential completion. And once we have computed the scores for all words against each other, we divide this score by 8. You may say, why 8? It may seem arbitrary, this 8, but it is the square root of 64, and 64 is the length of a query, key, and value vector, and the authors of this article used this number to normalize the scores. But you can change it, no problem. But after this division, the value are passed through softmax to normalize the scores, and now they add up to 1, acting as a weight. Using these weights, we multiply the value vectors of all words. Then we sum up these weighted value vectors, creating the output. This calculation are performed simultaneously for all words. Now you know all the process in a self-attention layer. But another point here is multi-attention conducts this process 8 times. Why 8? Again, you can change it. It can be adjusted. You can change this 8. But this approach enables the model. The reason is this approach enables the model to focus on multiple words within a sentence, not just the main one. But the problem is, if we perform the same operation 8 times, so we've got 8 different matrices, how we can manage them. To manage this, the approach proposed in the paper is to concatenate all of these matrices and multiply them with another weight matrices, and these matrices need to be trained, like biases and weights. It can solve the problem. This process yields a single output matrix for the attention layer. Let's repeat the example from the beginning of the workshop. Some cells appear bright, indicating high attention, while others are gray, suggesting lesser attention. But why? This example demonstrates that the model focuses on various words, not just main one. And it is our formula for transformer, and we can summarize all of this here. But if I want to summarize the whole process, it will be like this. Converting the input into the embedding vector, adding positional encoding, and multiplying the Q and K vector, query and key vectors. Dividing by the scale factor, applying softmax and obtaining the attention vector, and multiplying it by the value vector, and that's it. It is a whole process that we have talked about it until now. A language can simply rearrange the order of the words. For instance, the sentences Jane when looking for trouble and trouble when looking for Jane, they convey different meanings due to the word order. As a result, the language model must understand and account for this order. The current neural network attempt to do is by examining one word at a time during the process. However, they can't be fast enough. As previously mentioned, positional encoding adds information to word embeddings, indicating the position and order of the word. But as I said before, I don't want to talk more about positional encoding. There is a cosine and sine functions for this positional encoding in the original paper. You can read more about it. But in point cloud, this is really easier. I'm gonna pay attention to the method that we got in the point cloud and its difference from here. So far, we have tried to review the article attached with all you need and the most important parts of it. In the second part of our workshop, we will see how transformers can be used in point cloud tasks. And feel free to ask your question. Whenever you have a question, ask me your question. I will try to answer your question, definitely. Point cloud. What exactly is a point cloud? In a simple definition, point cloud is a large number of points gathered together, and together they may form an object that we are looking for. The label of that object. Now we want to discuss how we can use the transformer structure to perform the tasks in point cloud, such as classification and segmentation. And I want to start with the attention-based point cloud age sampling or APES article. Because there is a transformer structure in almost all of the blocks, it can help us to understand transformer and the structure of transformer in point clouds. The idea of this article, which is inspired by the existing method for the processing two-dimensional data, is that age points are always more important than the other one to identify the label of the object, for example, in classification task. But of course, I don't want to talk about their idea. I want to talk about how they could use transformer in their structure. But I strongly recommend you to study this article. This article, they have got an interesting idea, and their code is very clean and readable, and it can help you to understand this concept very well. You can see the network for classification and segmentation presented in the APES article here, and we are going to see all blocks used in these networks and see how the transformer structure is used in all of them. We'll start with the green block, and we can clearly see query key and value vector here again, like always. First of all, as you can see, the input blocks has dimension of n by d. N is the number of the points, and d is the number of these points dimension. And I must point out that the dimension of the raw data is always 3, because we live in a 3-dimensional data, and we have the 3 points in 3D space. But in the orange block, as you can see, or embedding block, we increase the dimensions of the data with MLP. For example, from 3 to 64, or maybe I think in this article, if I can remember exactly, they increased data from 3 to 128 in embedding block with an MLP, right? Nothing special. After entering these points, a k nearest neighbor is applied to them to obtain the neighborhoods, and we find up to k neighbors for each point's neighborhood, and then subtract the value of the neighborhood centers from the all neighbors within the neighborhood. I know it may seem a little bit technical, but we usually get neighbors with k nearest neighbor method or bar query method in point clouds, and it is usual and nothing special. And then after finding these neighborhoods, by applying MLP on the obtained tensor, we get query and key vectors. Also, value vector is obtained by only applying MLP on the input of the block. Okay, now we have got our vectors, query, key, and value, like always and as the lecture orders. Now the rest of the process is very similar. Now I want to ask you to keep in mind the main structure of transformers, and the rest of the process is very similar to the original transformer process. Let me explain. After multiplying the query and key vectors, we calculate the scale factor and divide the resultant multiplication by the scale factor, and then we apply softmax on it. After applying softmax, the attention vector will be obtained, and that's it. As a result, we multiplying the attention vector by value vector, we give importance to the values of the value vectors, and now this makes sense. Now we have implemented the transformer structures for point cloud tasks, either classification or segmentation. It is really easy, right? You need to know the main structure, and after that you can implement it everywhere. But of course it's got some details that you need to know about them. Yeah, I also put the code of this block here. After understanding the concept of this block, understand the code will be very simple. And I know that these kind of codes have got a lot of details and a lot of classes, functions, or details. And we haven't got enough time to explain. We haven't got enough time to talk about all of them. But I want to briefly look at the classes which is used to implement transformer in this block. So, but if you're interested in having a session code session, let us know. We'll try to have another code session and have a full review of these kind of codes as another workshop. Okay, now let me explain this code. I believe that code helps us to understand everything really better. Let's start with line 3. After calculating the relative neighbors in third line, line 3, in the fifth line, by applying MLP on the points, the query vector is obtained. And in the next 12 lines, the key and value vectors obtained by applying separates MLPs. Note that with the split heads function, we try to use several heads, similar to multi-head attention that we talked about it before. And I think, if I can remember correctly, 4 heads attention has been used in these codes, in these articles code. Sorry. Then the process inside the orange rectangle is like this. The query and key vectors are multiplied together to calculate the score vector, And then exactly like what we said in the first article, right? Again here. The score vector is divided by the scale factor, and after applying softmax, the attention vector is obtained, which is used as weights to apply to the values of the value vector. And that's it. It's very easy right now. Okay, there is a structure very similar to the block. We have talked about it in other blocks. As you can see here, we have got transformer structure in all of its block and nothing special. You can study, you can focus on these blocks and understand them completely. Right, while I suggest you to read the APES article that we have talked about it and we explained about it before, I want to review the two other articles as well. In point transformer version 1, we have this structure for classification. At the beginning of the model, we have a lot of 3D points, and finally we're going to find the labels of this point, the label of these points, so these points label. And you can see a lot of blocks here. The network structure blocks are common in point cloud. Don't worry about them. But the main idea is in the block with pale yellow color called point transformer. That I'm going to talk about point transformer. I'm going to explain point transformer for you. And of course, for segmentation, this structure is proposed in this article. And again, the pale yellow color block called point transformer is the most important one here. Let's see what's going on in point transformer block. This is the point transformer block structure. As you can see, there are three branches, like always: query, key, and vector. Query, key, and value vector, similar to the structure that exists in previous articles. And there is also positional encoding here, and I've gotten a slide for positional encoding. I'm going to explain positional encoding in point clouds. Interestingly, okay, regarding to positional encoding, this explanation given in this article. 3D point coordinates themselves are a natural candidate for position encoding. But why? I want you to think about this sentence a little. Easy answer, because with position encoding we are looking for the address for words, the order of the word, the position of the word. And when we're talking about 3D point coordinates, there are some address, 3D point coordinates and the addresses of the points itself. So we don't need anything special here. Let me read it again completely. 3-point coordinates themselves are natural candidates for position encoding. We go behind this by introducing trainable parameterized position encoding. Okay, now I'm gonna explain this formula for you. It's easy. Pi is the points themselves, right? 3D dimensional points themselves, and Pj is the close neighbors of these points that are subtracted, and then an MLP layer is applied of them. Now you can understand how we can use a position encoding in point cloud. It's really easier, and it's really easier than using this concept in NLP because of the inherent nature of point cloud, I can say. Now we know almost all these parts, I think, and they are familiar to us. We have positional encoding and other parts. Let's start with positional encoding again. The green rectangle, or I don't know, maybe it's a green square. We have a positional encoding which can be done in a simpler way according to the nature of the point cloud data. We subtract the value of the points and the neighbors, as I said before, and then apply MLP on them, and that's it. Positional encoding is done and it's ready to add the rest of the process. And in the part that is limited by blue line, you can see how to get the attention vector before applying softmax. The process is the same as before, nothing special here, with a slight difference that is not clear in the shape that I'm gonna explain to you. As you can see, there is a gamma sign here, I think. Let me continue from the beginning of the bottom part of this shape. Let me continue from this part, and then I'm going to continue. I'm going to explain about gamma sign. The query and key vectors are obtained, and here we don't multiply them as before with the gamma sign. But also we have a subtraction here, and then we apply MLP again on the result and add it to the positional encoding vector, and finally by applying softmax we get the attention vector like before again, and very finally we have a dot product with the value vector. And let me tell you something about this dot product. For those who want to study these articles, I need to explain that we've got two types of attention. scalar attention and vector attention. And of course, we have got another type of attention in point transformer version 2, which is group vector attention. And if you're gonna study these articles related to point clouds, I recommend you to pay attention to these different type of attention mechanism. Point transformer version 2 is an improved version of version 1. As you can see, there's a general formula that presents its general form. We create the query, key, and value vectors like always. Do the same calculations as usual. You can see some differences here, but the main structure preserved here again. Right? But before the end, I'm gonna finish this workshop. But before the end, let's take a look at the point transformers code, similar to the previous one. I have to emphasize that these kind of code have got a lot of details, but if you're interested in, if you would like to have another code session, let us know, and we're going to be sure and let us know, and we're going to coordinate another workshop in the code session and talk about these kind of codes. It is interesting for me. I'm eager to do that, but it depends on you. We start by applying MLPs on the features to obtain the query, key, and value vectors again, like always. In line 8 and 9, the neighborhoods are calculated, with the difference that in line 8, we add 3 dimensions related to the initial points, which in line 11 are used for positional encoding. I know it may seem a little bit complicated, and we need to debug this code and check the dimensions to understand it completely. But anyway, I can explain it right now. In the line 14, MLP is applied to the relative neighborhoods, and as I said in the diagram, the gamma sign means subtraction. Therefore, in line 16, we subtract the query and key vectors, and in line 19 we pass them to an MLP, or we send MLP on it, or we pass them an MLP. And finally, in the orange rectangle, we apply softmax and apply the obtained weights of the attention vector and the value vector, and that's it. As the very last point, finally, it is recommended to read these articles, and for sure reading their code can be very helpful and can help you to understand this structure and these concepts very better and deeper. Okay, this was an introduction to the story of transformers in point cloud, and I hope it has been useful for you. Thank you again. If there is any question, I would be grateful to answer your question. And I think there isn't any other question. I hope you enjoy your life and be happy. Thank you for your participating in this workshop. It has been really nice speaking to you. I hope to see you again, and goodbye.